Hello again. As you know, I'm Eli the Computer Guy over here for Everyman IT, and today's class is TCP/IP and subnet masking. So today we're going to be talking about the TCP/IP protocol and then how you create subnet masks. So this is important in today's day and age. TCP/IP is the main protocol that is left for networking. Back when I started 10 or 11 years ago, there were lots of protocols that people used. People used TCP/IP. People used IPX, SPX. They used NetBEUI. They used numerous protocols. Now, just about everybody uses TCP/IP. Now, the class today, we are going to be talking about something called TCP/IP version 4. So there are multiple versions of the TCP/IP protocol. You may have heard of something called TCP/IP version 6. Well, so that you understand, TCP/IP version 6 is much different than TCP/IP version 4 as far as things like configuration goes. Actually, well, it's a lot different on a whole bunch of things. But as you should understand, if you know how to do TCP/IP version 4, you don't necessarily understand how to do TCP/IP version 6. This is not a big deal. I know if you read the technology papers and the magazines and all of that, you will hear that TCP/IP version 6 is the next great thing, and we all have to jump on the TCP/IP version 6 bandwagon, and if we don't, it's going to be computer Armageddon. Honestly, I have been hearing that since 1999. Way back when I got my MCSE, my Microsoft Certified Systems Engineer, way back then in 1999, they were telling us how everybody was going to go to TCP/IP version 6 like in the next couple of years. And now it's 11 years later, and everybody is still using TCP/IP version 4. So if you learn TCP/IP version 4, you're good. We're going to be using this for a long time. At some point, TCP/IP version 6 will replace version 4, but you know, I mean, that could be 2020, or at the rate we're going, 2030. So, so you'll be fine. We're going to be talking about TCP/IP version 4 today. We're going to be talking about how it works, and again, we're going to be talking about how you do subnet masking. So when we are talking about the TCP/IP protocol, you have to understand a few things about how TCP/IP works. This will just make things easier as you go on in networking. The first thing that you need to understand that the TCP/IP protocol is actually what is called a protocol suite. The TCP/IP protocol is actually made up of something called TCP protocol and IP protocol. Actually, with a few more protocols in there. The TCP/IP protocol is multiple protocols all tied together into one thing that is called TCP/IP. The main protocols in here, though, in TCP/IP are TCP, which is Transmission Control Protocol, and IP, which is Internet Protocol. Now, these are the main protocols, and they do two very important functions. The first protocol that we should talk about is IP. So what IP is IP is the protocol within TCP/IP that controls routing of information to different computers, different devices, and different servers on the network. So you will have heard of IP addresses. The IP protocol deals with these things called IP addresses, subnet masks, default gateway, DNS, etc. The IP protocol is what allows two computers to figure out where the other one is so that they can start communication. The big thing with IP that you will hear is that IP is what is called a routable protocol. Therefore, TCP/IP is a routable protocol. Back in the day, like I say, when there were more protocols out there that people were using, there were routable protocols and non-routable protocols. So routable protocols were TCP/IP, IP, IPX, SPX. What this meant was that you could divide networks into multiple sub-networks. So in non-routable protocols, every single computer can talk to each other. They're all connected. So if you plug it into a network for a non-routable protocol, all those computers are connected. And this can cause absolute havoc with just bandwidth utilization when all these different computers try to talk to each other. Because imagine if every single computer on the entire internet was actually connected to every other single computer on the internet at any one time. It would be complete havoc. Take my word for it if you don't understand why. What IP, which is a routable protocol, and IPX SPX did, was they made it so that you could divide all these computers into multiple subnetworks. And then you had a boundary, which was your router. And then through that router, these computers could then try to connect to other networks if need be. So anything on this subnetwork would talk to each other. But if a computer here needed to talk to another subnetwork, then it would go through a router, it would go through the internet and such, and go to the subnetwork. Basically, routable protocols allow for you to divide huge networks into smaller subnetworks. This is a big thing. Then, being a routable protocol, you connect all of those subnetworks using routers. Yeah, makes sense. So that's the big thing with the IP protocol. Now, of course, the IP protocol, just so you know, since we're doing a class, when we talk about the OSI model, so the OSI model is the model for how network communications happen. IP is on OSI layer 3, the network layer, just so you understand that. So once we've talked about IP, so IP is about routing the information. So it's how computers discover each other so that they can start communicating. Well, once the computers have found each other, then they do need to start communicating, and that is where TCP comes in, Transmission Control Protocol. So this deals with once the computers have found each other, how are they going to talk? So hello, hi. Okay, now that that's happened, how are they going to talk? You know, what language are they going to talk? How fast are they going to talk? Etc. This is all done with a transmission control protocol. Now, you can get into a 5-hour class just on explaining all this basic stuff. But what you should understand about TCP that becomes very, very important, especially as a network technician, is something called windowing. Windowing is the process by which the client computer sends information to the server computer. So when two computers are trying to talk, windowing is the process of how that data is sent from the one computer to the other computer. What happens in the windowing process is you have one computer here and you have one computer here, right? Remember that when TCP/IP was created, when the internet was created, this was created for the military. This was created for World War III scenarios. Everybody thinks this is a joke. Everybody kind of laughs at it. But no, remember, the internet, TCP/IP, all of this was created so what happens if nuclear Armageddon has happened and you have diverse military installations trying to communicate with each other. I mean, that's a scenario that TCP/IP was created under. So under that scenario, the government and the military realized that lines of communication might be very, very flaky. You may not be able to send a lot of data, because if you sent a lot of data, by the time it got to the other side, wherever it's getting sent, it may be garbled. So what they came up with was a concept called windowing. So what happens in windowing is this computer, computer 1, is trying to send information to computer 2. Now in TCP/IP, all the data is broken down into something called packets. So if you're trying to send a Word document, if you're trying to send a movie, etc., all that gets divided down into these little packets. Those packets then get sent to the computer that is receiving the data. Well, since the computers don't know what the quality of the transmission lines are, the first computer doesn't want to just send the entire document all at once because it may come out as garbage at the other side. So what it does is it starts sending packets in groups, and those groups get progressively bigger. So what happens in the windowing process is computer 1 will actually send one packet all the way over to computer 2. And this packet will be labeled packet 1. Computer 2 will receive packet 1. It will send an acknowledgement back to computer 1 saying, hey, I received packet 1. So that's only one packet, and a packet is really small. It's like bits and bytes. It's nothing. But now that computer 1 understands that it can talk to computer 2, it knows that it can try to send a little bit more information. So this time, it will send packets. Since we already did 1, it will now send packets 2 and 3. So it now sends 2 packets over to computer 2. Computer 2 receives those 2 packets and it says, hi, the last packet I received in order was packet 3. So it sends back an acknowledgement, said, I received packet 3. Then computer 1 goes, hey, this is even a better connection. So what I'm going to do is, that was 1, 2, 3. So I'm going to send packets 4, 5, 6, and 7. So now it sends 4 packets. So this is theory, but let's say it doubles every time. This goes to computer 2. Computer 2 goes, hey, I got all the information. The last packet I got was 7. So an acknowledgement goes back to 7. So this is great. So basically, as long as this communication is solid, as long as this keeps happening right, computer 1 keeps sending out twice as much information. So the next time it'll send out 8 packets, then it'll send out 16 packets, 32 packets, 64 packets. And as long as it's receiving the acknowledgement on the last packet and that it's in order, then it will just keep doubling and sending out larger and larger and larger chunks of this information. Now, what happens is, let's say this gets up to 128 packets, that it's sending out to computer 2. Now, if something happens with the data on the way and the packets get messed up, what may happen is computer 2 will only receive, let's say, 2 packets out of that whole mess of 128 packets. So computer 1 sent 128 packets. Computer 2 only received 2 of those packets in order. So let's say at this point, packet 1034 or 1033. What will happen is computer 2 will then say, hey, the last packet I received in order was packet 1034. What computer 1 will now do is it will start sending information again, and it will close the window back to a single packet. So now we're all the way up to sending, 256 or 128 packets, large chunks of data. Well, now, since computer 1 knows there's a problem, it will now go back and it will send 1035. It will send a single packet to computer 2. And then computer 2 will say, I received 1035. And then computer 1 will then send 2 packets. And then computer 2 will say, I received those 2 packets. 4 packets, I received that 2. And this keeps happening until there's a problem in the data communication, and then it goes back to sending 1 packet, and then 2 packets, and 4 packets, and 8 packets, and then back to 1 packet. So basically, every time there's a problem with the transmission, you go back, computer 1 goes back to sending 1 packet, and then it starts expanding the window, and then if there's a problem, it brings the window back down again. It starts expanding the window, brings it back down again. Now, if you were like me and you were using the internet back when we had 56K modems and 28K modems and all of that, you used to see this windowing a lot. So, if you're 30 years old or older, you've probably seen this happen. So back when you used to download information from websites, you would have a little progress bar. And on that progress bar, you would see where it would incrementally download, like it would be like, it'll download, 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 and so it would like stutter. So it would be like small increments and then huge increments, small increments and huge increments. The reason you saw that was because of the windowing that was happening during that communication process. Why windowing is huge right now in today's day and age? Because you're like, Eli, modems. I know some of you probably have never used modems. So you're like, Eli, I don't care about it. 56K modems? Why do I care about that? Why this is important in today's day and age is because of real-time communications. Because TCP/IP version 4 can be a real mess for real-time communications, because that whole windowing process, when you're sending pictures, you probably don't notice it if you have a broadband connection. If you have a 3 megabit per second connection, you just see videos download. You just see pictures download. Even if there are little quirks or little stops in it, it's still so fast you do not see it. Real-time communication has to happen in real time. But the problem is if there are any problems or hiccups on the network, with this windowing process, you can have the sending computer go down to sending 3, 4, 8 packets at a time. 8 packets is not enough to keep a real-time communication stream going. Again, this gets a little complicated for this class. The more you play with networking and such, the more you will understand this. The main thing to understand with the transmission control protocol is that this is what actually controls the communication. So IP connects two computers together. TCP is what then deals with the communication between the computers once they've started talking to each other. The biggest concept out of TCP you have to understand, though, is this thing called windowing. This is how data is transferred from the first computer to the second computer. What you have to understand is basically it starts out with one packet, it doubles, it doubles, it doubles, it doubles until there's a problem. Then it goes back to 1, double, 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 double until there's 1, double, double, double until 1. See how it goes? Hope you know how it goes. But those are the things that you have to understand when you're dealing with a TCP/IP protocol suite. Remember, it's an entire suite. And of course, just so I do my due diligence, TCP is OSI layer 4. So this is called the transport layer. Transmission control protocol, transport layer, all makes kind of sense. So let's talk about the components of a TCP/IP network, so you understand, what you're looking at when you're looking at a TCP/IP device. The first thing is what is called the IP address. So the IP address is something that you'll see, and you'll see it's like 10.1.10.1, let's say. That is an IP address. IP addresses are addresses that are used to signify every computer or device on a network. Every computer or device on a TCP/IP version 4 network needs an IP address. 10.1.10.1, 192.168.1.1, etc. 207.65.44.1. These are all IP addresses. So every device on the network needs what is called an IP address. So then, after you have the IP address, you have something called the subnet mask. Now in the next section we're going to talk a lot more about the subnet mask, so we're just gonna just kind of glaze over right here. The subnet mask is basically a way to segment a network logically so that different computers and different devices cannot necessarily talk to other computers and devices on the same physical network. So basically, if you have a large network, let's say you have 200 computers on a network, you don't necessarily want all those computers to be able to talk to each other, even though they're physically connected to the same network. You can prevent them from talking to each other by putting in this thing called a subnet mask. And the subnet mask, again, like I said, we're going to talk about it in the next section a little bit. Now, the next thing after you deal with the subnet mask is something called the default gateway. The default gateway is the router for the subnetwork that you are on. So basically what the default gateway allows is your computer is going to look on the local network for the computer or device that it's looking for. Let's say it's looking for a website or it's looking for a server. It's going to look at the local network first. If it can't find that computer or device on the local network, it will then go to the default gateway and it will ask the default gateway to find that computer or device on whatever else is on the other side. So basically what happens is, you have your office here and you have the internet out here. You have your computer and you have your router. So what happens is your computer with its IP address is looking for a website. Now this may seem a little funny, but basically it's looking for a website. And what it will do is it will first look at all the computers in the internal network looking for the website. So if you're trying to go to www.cnn.com, that computer is actually going to look inside your little subnetwork to see if cnn.com is there. If it's not there, it will then use this default gateway. It will then go to the router and say, hey, I need to find cnn.com. That router will then go out to the internet, and through the whole bunch of magic of the internet, it will then find cnn.com, and it will create a link between cnn.com and your computer. So the default gateway is the router. If you're dealing with small networks, this will be the router, this will be the DSL modem, this will be the cable modem, this will be the ADTRAN, etc. Basically, the default gateway is what connects your subnetwork to all the other networks that are out there. So you understand what the default gateway is. Now, the next big thing to understand is we were just talking about www.cnn.com. Now, if you've been paying attention to what I've been saying, the Internet Protocol, the IP protocol, connects computers based upon their IP address. So 10.1.10.1, let's say. Now, this is not this. So you may be wondering, well, if all the IP protocol cares is about these IP addresses, well, where do these domain names come from? www.cnn.com, server, if you have computer names, PC1, etc. Well, CNN.com actually doesn't mean anything to your computer. So your computer that you're sitting in front of, when you put in www.cnn.com, your computer actually does not care about that for TCP/IP communication. What it cares about is the IP address. So what happens is you have your computer, and your computer only cares about an IP address. But you want to plug in something like CNN.com. This is where something called a DNS server comes into play. This is called a domain name server. What domain name servers do is they map domain names to IP addresses. So within this domain name server, it will say www.cnn.com equals, 201.65.33.2. So what's going to happen is you plug into your computer, into your web browser, www.cnn.com. Your computer doesn't care about this name. Can't really do much with it. But what it can do is it can take CNN.com, it goes and it talks to the DNS server, and it says, hey, this guy just plugged in www.cnn.com. What does that mean? The DNS server then tells your computer that CNN.com is the IP address 201.65.33.2. Your computer then goes, oh, thank you. I now know what to do with that. So it then uses this 201.65.33.2 IP address. It then looks at the internal network for the IP address. If it can't find it in the internal network, it then goes to your router, to your default gateway, and your default gateway then goes out to the internet and then connects your computer. So the important thing to understand here is when you put in CNN.com, Facebook.com, Yahoo.com, etc., 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 your computer really doesn't care about that. That is for you. Your computer would prefer you plug in IP addresses all the time. It would make life a lot easier for your computer. Thankfully, the world isn't run by computers. So what happens for your computer, because your computer only cares about IP addresses, what happens is when you plug in this is called a domain name, when you put that into your computer then goes out, it talks to the DNS server. The DNS server then tells your computer what the IP address is of this domain name. Once your computer has the IP address of the domain name, then it can go out and it can try to find the website that you are looking for. This is a simplistic thing. Once we get into website administration and all that, this gets a little more complicated, but this is the basic idea. Your computer does not care about domain names. It resolves domain names through DNS, a domain name server, to get the IP address of the computer with this domain name, and then once it has the IP address, it then goes out to communicate with that computer. Now the final component that you need to understand about for TCP/IP networks is something called DHCP. I think it's Dynamic Host Control Protocol. Now, what is this? Well, as I've said, every device on the network needs an IP address. If it does not have an IP address, it can't do anything. Not only can it not receive communications, but it also cannot talk to everybody. So every computer on the network needs to know its IP address, it needs to know its subnet mask, it needs to know its default gateway, and it needs to know what DNS servers to talk to. So there are two ways you can give this information to the computer. The first is by giving your computer what is called a static IP address. What this means is you sit down at your computer or the device and you plug in all the information manually. So you say this computer has an address of 192.168.1.55, has a subnet mask 255.255.255.0, has a default gateway of 192.168.1.1, and the DNS servers are 192.168.1.1 and 208.55.44.1. Now, as you can see, me simply writing this out on a whiteboard, and that took a couple seconds. You were probably getting a little bored while I was doing it. So this can be a real pain in the butt. If you have to sit down at every single device on a network and plug in an IP address, this can be a real problem. Not only that, but since all computers on a TCP/IP version 4 network are signified, are communicated with their IP address, if you accidentally give two devices or two computers the exact same IP address, it can just cause all kinds of havoc. So some packets go to that computer, some packets go to that computer. I'm not saying some documents go to one computer and some documents go to the other computer. Like I said, when computers are communicating using the TCP/IP protocol, things like documents, things like videos, things like pictures get divided into packets. It might take 1 million packets to put one picture back together. So if 500,000 packets go to one computer and 500,000 packets go to the other computer, there's nothing there to rebuild. So this is very important to understand. So if you have two computers on the same network with the same IP address, that's just bad. It's just not gonna work out very well. So what you can do is you can give the computers or devices on your network what are called dynamic IP addresses. And this is where DHCP comes in. So dynamic IP addresses mean that when the computer connects to the network, it will call out to the DHCP server. The DHCP server will then give it an IP address, it will tell it the subnet mask, it will tell it the default gateway, and it will tell it the DNS servers all automatically. And it will keep a record of the IP addresses that it has given out to make sure that it doesn't give out the same IP address to multiple computers. This is a huge thing. So basically DHCP allows for the automatic distribution of IP addresses and the information, like I say, with subnet masks, default gateways, DNS, etc. This is a very good thing. Again, you may not realize it on a 5 or 10 computer network, but once you start dealing with hundreds or thousands of computers, this is DHCP is a lifesaver. Now what happens in the DHCP process is that your computer, so we put your computer here again, calls out to the DHCP server and it says, hey, I need an IP address. So you have configured in the DHCP server what the scope of IP addresses the DHCP server can give out. So you will tell the DHCP server, you can give out IP addresses 192.168.1.100 through 254. So this gives it a scope of 154 IP addresses that this DHCP server can give out. So this DHCP server will not give out 192.168.1.0 .99 because that is not within its scope. It will give out .1.105, .110, .205, etc. So the scope is the full range of IP addresses you allow the DHCP server to give out. You will then tell it what the subnet mask is. Again, we're going to go into this in a few minutes. And you would say 255.255.255.0, a class C subnet mask. You would tell it what default gateway you want it to give computers, you know, so 192.168.1.1. This is the router, so how they're going to communicate with the outside world, and then what DNS servers that you want to tell the computers about, you know, again, whatever that is. So your computer talks to the DHCP server and gets all this information. You have configured, or somebody has configured all this information in the DHCP server at some point in the past. Now, the DHCP server will then give all this information to your computer with something called a lease time. So what the lease time means is this is literally a lease on how long your computer is allowed to own that IP address. So your computer asks for an IP address. That IP address and all that information is given to your computer with a lease time. This lease time may be a day. This may be 7 days. It may be a month. It's all up to you as a system administrator. This, again, is something that you configure into DHCP. Well, DHCP server gives your computer all the information with this lease. So let's say it's 4 days. What happens is halfway through the lease, your computer tries to automatically renew the IP address. So, you know, you get this lease for 4 days. At the 2-day mark, your computer will automatically recontact that DHCP server and say, hey, I am still here. I'd like to keep the IP address. Do you mind? DHCP server says, nah, no problem at all. You keep the IP address. So, and then the lease is renewed for another 4 days, and the computer keeps the IP address for 4 days. Again, at the 50% mark, the computer then contacts the DHCP server again and says, hey, I still like this IP address. Am I allowed to keep it? DHCP server says yes or no. Well, what happens is if your computer cannot contact the DHCP server at the 50% mark, then it waits until the next 50% mark. So you have a lease for 4 days. So at 2 days, your computer tries to automatically contact the DHCP server and say, hey, can I keep this IP address? If for some reason the DHCP server is offline or cannot be communicated with, then your computer keeps the current IP address that it has, and then it waits till the next 50% mark. So you started at 4 days. At 2 days, you asked for a new IP address. You didn't hear back. So at 1 day, you ask for a new IP address. If you still don't hear back, you wait another 50% of the time. So this is down to 12 hours. So at the 12-hour mark, you try to contact the DHCP server. If it doesn't communicate back, then at 6 hours, you try to talk. Then at 3 hours. So every 50%, it tries to recontact that DHCP server. Finally, when it gets all the way to the end, it really kind of depends upon the networking software that you have installed on your computer. Sometimes it will flush out the other times it will keep it. So the big thing to understand is that for DHCP, this is all dynamic. As soon as you plug your computer into the network, it will try to communicate with the DHCP server to get the IP address, the subnet mask, the default gateway, DNS, etc. DHCP server, as long as it's there, will give that information along with a lease. Again, the lease is something you configure. It can be 1 day, it can be 7 days, it can be a year. It's all whatever you plug into the server. The big thing to understand is at the 50% mark, the 50% from when the lease is going to expire, your computer is going to try to contact the DHCP server to ask if it can keep the IP address. So if this is a year, if the lease is a year, then at the 6-month mark, it will try to communicate. If it's 2 days, then at the 1 day mark, it'll try to communicate. If it can't communicate, then it will wait another 50% of the time. So then, you know, like I say, if it's 4 days, then it'll go to 2 days, then it'll go to 1 day, then it'll go to 12 hours, then it'll go to 3 hours, then it goes to 1.5 hours, then it goes to 45 minutes. and then the math, 22 minutes and 30 seconds, so it keeps dividing in half. This is something important to understand with DHCP servers. Now, most DHCP servers, they normally give out a lease of about 7 days, and this is a good default. What you have to understand is once you get into more complicated networking, is the shorter your DHCP lease, the more network traffic you have, just for stupid things like DHCP, but it means that less IP addresses are being used by computers that may not be on the network. Whereas the longer the IP address, the more IP addresses get used up, but the less traffic on the network. That's kind of something that you'll have to deal with, some other point. We'll talk about that later. Now, the final thing that you should understand. So we've talked about DHCP, we've talked about DNS, we've talked about default gateways and all that. The last thing that you should understand is something called network address translation. It's called NAT. You will hear about NAT a lot. So back in the days, 15 years ago, everybody was worried because they thought that every single computer device on the internet was going to require its own dedicated IP address. So that means your computer would require an IP address that was unique to the world. Not unique to your office, unique to the world. Your printer, your network printer, would need an IP address that was unique to the world, etc. Because they thought every single device that was connected to the internet would need its own unique IP address. Well, then they came up with something called NAT, or network address translation, and this fixed a whole bunch of stuff. So you will see, this is our router, that most internal networks have IP address ranges in the 192.168.1.1 to 254. So, if you go to your little network inside your house, your computer inside your house may have an IP address of 192.168.1.2. You can go to your friend's house, and one of the computers inside his house also has an IP address of 192.168.1.2, etc., etc., etc. How this happens, or how this is able to work, is through network address translation. What happens is every router that connects to the internet, so whether this is a home router, whether this is a business router, whether this is an enterprise, whether you're dealing with IBM, every single router that connects to the internet needs its own dedicated IP address. So this building that Everyman IT is housed in, we have an IP address. Our computers, our servers that are sitting on the internet, they have individual IP addresses. My home router has an individual IP address. But then, once you get inside the router, you can use, or you can reuse IP addresses. So, like I say, all internal networks either use 192.168.1. whatever, or they use 10.1.10. whatever network addresses. All the internal networks. Because what happens is, let's say you have a computer here, it's 192.168.1.2, and you have 192.168.1.3 here. So this is your network. Then your neighbor has 192.168.2 also, and 192.168.3 also. Well, when you are trying to communicate to servers on the internet, the server that is on the internet is going to be most worried about what your external IP address is. So your external IP address will be, say, 208.55.44.1. So what network address translation allows is computer here, this 192.168.1.2, is going to go to your default gateway, and it's going to go out and it's going to find CNN.com. CNN.com is then going to say this communication came from this particular router. It will send the information back to this router. This router has NAT built into it, network address translation built into it, and it says, I know that internally the computer that was asking for this information is 192.168.2. And so it will then route the information to 192.168.2. Now, if this computer down here wants to go to, let's say, facebook.com, the external IP address for this router may be 209.77.66.44. So 192.168.3 is going to go to the default gateway, to the router. That's going to go to the internet. That's going to go to Facebook. Facebook is going to go, oh, I see the person requesting this information is this external IP address. So Facebook will send the data back to this external IP address. NAT, network address translation, is built into this router. This router goes, oh, I see that 192.168.1.3 is the one that asked for this information, and then the information will get routed here. Again, this is a whole mess. NAT is not a hugely complicated subject. You know, maybe you should go on Google or Wikipedia if it's a little confusing. The main thing that you have to understand that NAT does, network address translation, is it makes it so every single device that can talk on the internet does not need its own absolute unique IP address in the entire world. If NAT did not exist, then literally every single device that connected to the internet would need its own IP address, and simply there are not enough IP addresses out there. So with this, we've talked about the IP address. Every single computer or device on a TCP/IP version 4 network needs an IP address, both to send and receive information. We talked about the subnet mask. This is how you subnet. We'll talk about that more in a second. We talked about default gateways. Default gateways are routers. Routers are what connects different sub-networks. So whether you have multiple sub-networks in one building or whether you are trying to connect your little office network off to the internet, the default gateway or router is what separates those two networks. We talked about DNS. Remember, domain names, CNN.com, Facebook.com, Yahoo.com, etc. don't mean anything to your computer. Your computer will go out and talk to a DNS server and it will say, hey, my user gave me this name. What do I do with it? That DNS server will then say, IP address for that domain name is this, 208.77.66.4. That gets given back to your computer. Your computer then tries to communicate with the website or the computer based upon that IP address. We then talked about DHCP, Dynamic Host Control Protocol. Again, you can plug in what are called static IP addresses into every single computer and device on your network. This means you sit down at every single computer and you actually type in what IP address, what subnet mask, what default gateway, what DNS server, etc. Or you can set up DHCP. DHCP will automatically give all of this information to any client that connects to the network. Now when it does, remember that it gives all that information, and it also gives a lease time. A lease time is something that you can configure on the DHCP server. It could be a day, it could be a year. It's all up to you. The average is like 7 days. Once that lease is 50% expired, the client will try to recontact the DHCP server to renew the lease. If for some reason the client cannot contact the DHCP server, it will wait till the next 50% mark, to the next 50% mark, to the next 50% mark, etc. And then finally, in this whole mess, we talk about NAT, network address translation. Basically, this is what keeps, from having every single device on the internet needing its own IP address. That was a big mouthful. If you thought that was confusing, we're about to go into subnet masking. So you might want to pause here and get a little cup of coffee. Okay, so we're starting on the long uphill slog to subnet masking. Now the first thing, before we go into subnet masking, is you need to understand where we come up with these numbers. When we say 10.1.10.1, where does that come from? When we say 255.255.255.0, what does that mean? Well, basically, what those addresses signify is there are a number of values for what are called octets. So when you're dealing with TCP IP addresses, you're dealing with 4 octets. So octets are series of 8 numbers. So basically, you have 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8. So when I say, let's say 10.1.10.1, the computer is actually looking at this big thing, which is a series of 4 octets to come up with this number. So 10 would be here, dot 1 would be here, dot 10 would be here, dot 1 would be here. Now, when we're looking at this octet and where we come up with these numbers, so we'll look at a single octet. So 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. These are 8 bits. So with this, they can either be 1 or 0, 0 or 1. So you can have 1, 1, 1, 0, 0, 1. It can be 1 or 0. So on or off. You can't have 2. 2 doesn't work. It's either 1 or it's 0. Now, how we get to the numbers then is starting on the right-hand side, we give each one of these spaces a number value. So here, this number value is 1. The second one in is 2, and it keeps doubling. So 1, 2, 4, 8, 16, 32, 64, 128. So these are the number values for these octets. So this is 1, 2, 4, 8, 16, 32, 64, 128. Then if you go to the next octet, you start over again. So 1, 2, 4, 6, or 8, etc. So each octet is entirely separate. So if you are trying to get, let's say, an IP address of 128. So 128, what you would do is you would put a 1 over the 128 and then a 0 over everything else. So this means count 128. So if I want, 192.168.1.128, you would just put 1 bit as true over 128. If, let's say you're trying to get 192.168.1.10, right? Well, then we look here and we say, okay, well, we've got an 8, so we'll make 8 true. And then we've got a 2, we'll make 2 true. And then everything else is 0. So if you want 192.168.1.10, that means 2 has a 1 over it, and 8 has a 1 over it. Does that kind of make a little sense? So, if you want, let's say, I don't know, address 254. So if you add all these up together, they will come out to be 255. So 255 if you add up all these together. So let's say you want an IP address of 254. So you'd say 1111111 0. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2. That's it. And then you add all that up, and that will come out to 254. So this is what the numbers mean. This is how we get the numbers. This is going to be very, very important in a second once we start dealing with subnet masking. So basically, when you're dealing with an IP address or when you are dealing with a subnet mask, you are dealing with 4 separate octets. These octets are made up of 8 bits. The bits are either on or they're off, so 1 or 0. The way you come up with a number is, again, from right to left. You start with 1, then you double to 2, to 4, to 8, to 16, to 32, to 64, to 128. So all this will make a little bit more sense once we get into the subnet mask in a second, but this is the basic idea behind numbering and octets. So now that you understand how the numbering system works, we need to talk about subnet masking. So what you may not realize is when you're dealing with an IP address, let's say 192.168.1.1, this IP address actually tells you 2 things, or there's 2 things in here. One is the address of the computer or the networking device on the network. So whether it's a computer, whether it's a server, whether it's a printer, whatever the TCP IP address, the device on the network is, that is here. But there is also the subnet number or the network number. So the IP address tells you the identifier for the network, and it tells you the identifier for the computer or networking device. Now, you're looking at this number and you're probably wondering, what part of this is for the network and what part of this is for the computer. Well, that is what the subnet mask tells you. So you will see something like 255.255.255.0. This subnet mask tells you what part of this IP address is the network identifier and what part of this IP address is the device identifier. Now, this is very, very important because devices on different networks cannot talk to each other. So if you have one computer plugged into a switch on network 1 and you have a printer plugged into the exact same switch, so they're physically on the switch. So you have a switch here, one goes to a computer, one, let's say, goes to a printer, right? The computer that is on the first subnet cannot talk to the printer if it's on another subnet or another network based upon the IP address, unless, of course, there is a router to connect them. So remember, routers connect different subnets. So if you have a computer on one network and a printer on a different network, they need a router to communicate, even if they're plugged in physically to the same switch. So this is very important to understand. So you can have multiple subnets, multiple networks, all plugged into the same physical switch. And this is not VLANs. This isn't like Cisco VLANs or like routing or switching VLANs. This is simply how TCP/IP works. So if you have computers on different subnets, on different networks, even though they're connected to a switch, so they're physically connected together, they still cannot talk to each other. So this is very important to understand. So the subnet mask is what tells you what part of the IP address is for the network and what part of the IP address is for the device on the network. So this here is what is called a Class C subnet. Since I know what's going on, I can automatically look at this Class C subnet and know that the network portion of this address is 192.168.1. So this is a 192.168.1.x network. And I can tell that the identifier for the device on the network is the 1. Now I can do that because I understand what subnet masking is. So now that we understand how all that works. Now, how you figure out a subnet is basically you decide. So we talked about the numbering system before. So we have 4 octets of bits. A bit can either be a 1 or a 0, remember? And depending on how the 1s and 0s are up here, you get a different number. So like this 1 right here, in order to get 192.168.1.1, that means we have 0, 0, 0, 0, 0, 0, 0, 1. And that makes 1. If we wanted, let's say 3, it would be 1, 1, 0, 0, 0, 0, 0. So remember how we talked about the numbering system before. So what we do is, using these octets, we decide how many networks we need in our network, in our overall network, and how many hosts we need in our overall network. And then all we do is we use that many bits that we need to accomplish our task. So we just divide it off anywhere in here. So we can say right here, we want everything to this side to be the network number, and everything to this side to be the device number. Or we can come here and we can put it here. Or here, or here. It doesn't matter. We can decide depending upon the subnet mask. So when you're trying to figure this out, the thing to think about is it depends on how many networks you're trying to create or how many devices you're trying to shove into a single network. So depending on how many bits you use for your network, there is an equation, and for the networks it is 2n. So the total number of subnets you can have is 2 to the power of however many bits you have used for the subnet. So let's say you want to use the first 8 bits out of the 4 octets for a subnet. So it would be 2 to the 8th. And that will tell you how many subnets you can have on this network. Now, if we're trying to find hosts, so this way is for networks, this way is for hosts, you have 2 to the n minus 2. So let's say we wanted 254 hosts. That's a standard. That is using 8 bits from this first octet. So this is a class C subnet. So it would be 2 to the 8th minus 2, and I just know this by heart, which comes out to 254 hosts. So what you're doing when you're creating the subnet is you have to figure out either how many networks you want or how many hosts you want. And then, depending, you basically count one way or the other. If you need lots of networks, then you count out how many bits you need from left to right, and then you just take those bits for your subnet network. And to figure out how many subnets you can have here, it is 2 to the n. 2 to the exponent of however many bits you have taken. If you're trying to figure out how many hosts you need, you go right to left, and then you just take the bits as you need. And so 1, 2, 3, 4, 5, 6, 7, and you keep going, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, however many you need. So if you need, let's say 508 hosts on a, or no, it would be more than that. But basically, you just go across, and that way it is 2 to the n. So the n is how many bits you use, 1 or 2 or 3, minus 2 tells you how many hosts. So that's all you have to do to figure out the subnet, how many subnets or devices you need. Now, when you're dealing with this, all you do then to figure out the subnet mask is, again, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8. So these are the 4 octets. To figure out the subnet mask, you just add up all of the bits and then the number. So remember, when we're dealing with an octet, 1, 2, 3, 4, 5, 6, 7, 8, remember the number positions. This is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64, and this is 128, right? So, if we're trying to figure out a subnet, and let's say we decide to use all of the first octet for the network, for the subnet networks. So if we add up 1 and 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 1, if we add up all these, right, then that comes to 255. And then we do dot, because that's the octet, and then there's nothing here, and nothing here. So that would be 255.0.0.0. So the subnet mask, if you were doing this, would be 255.0.0.0. Now, let's say we wanted to do 111.111.111. So we wanted to use all of that, right? So then that would be 255.255.0.0. And if we wanted to use all of that, 11111, then it would be 255.255.255.0. So now you may have seen these particular subnets before. 255.0.0.0, 255.255.0.0.0, and 255.255.255.0. These are the classic A, B, and C subnets. So an A-class subnet is 255.0.0.0. A B-class subnet is 255.255.0.0. A Class C subnet is 255.255.255.0. So if you ever hear about this, when you have normal networking people all talking back and forth and they say, it's a Class C subnet, what they mean is that the subnet mask is 255.255.255.0. If they say it's a Class A subnet. It's 255.0.0.0. So you follow me there? Now, okay, so you've seen these standard ones, 255.0.0.0, 255.255.255.0. Well, sometimes, since you are going to be a really cool network engineer, you are not going to divide your subnets on the octet, right? So 1 octet, 2 octets, 3 octets, 4 octets. Sometimes you're just going to have to be crafty, clever, cool, and not use the 255 subnets. So let's say you were given a whole Class C subnet. So you are in an office, and your higher level network person gave you 254 hosts. So they gave you a Class C subnet, 192, let's say .168.1.x. And that's 255.255.255.0. So you're allowed to use this. But you want to divide this into 2 networks, right? Well, so we're using all the ones here, all the bits here, all the here. So let's say we just want to create an extra couple of networks. So we're going to steal a couple of bits out of this Class C subnet. So with this, all you do is, of course, because we use all the numbers here, that's 255, period. We use all the numbers here, 255, period. We use all the numbers here, 255, period. But here, we only want to use 2 bits. So then we do 1 here and 1 here, right? Because that's where the division for the subnet will be. We add that up, and then this subnet mask will be 255.255.255.192. So now we can use these 2 bits to create different networks. So that's how that works. Subnet masking is pretty confusing. You gotta scratch your head over it, and you don't have to do subnet masking very often. Normally, you simply use the subnet mask that, frankly, somebody else gave you. Whether it's your ISP provider, whether it's a senior level engineer, etc. You very, 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 very rarely have to create your own subnet mask, dividing it off here. I've probably done it 10 times in the real world in my entire life. You just use the subnets that they already gave you. The important thing to realize, though, is how to count how many different devices you can have on any particular subnet, because this will be important, especially in larger environments. Because, like I say, if you have a Class C subnet, so Class C is 255.255.255.0, that means you're using 8 bits for the device identifier, which means you have 2 to the 8th minus 2, which comes out to, you can only have 254 devices on this network. You try to plug in 300 devices, especially if you have something like a DHCP server, it's all gonna get nasty really quick. So this is an overview of subnet masking. Again, like I say, it's very confusing, very tedious. The main thing that you have to understand is when you're doing the subnet mask, whatever bits you use are used for the network, the subnet identifier. The other bits are used for the computer identifier. Why this is important, and this is the huge thing, so if there's one thing you take away from this, please take this, is if you have a switch here, you have a computer here and a computer here, and this is on network 1 and this computer is on network 2, they cannot talk to each other based on the TCP/IP protocol. You have to put something called a router in between these 2 computers to get them to talk to each other. So that's the most important thing to take out of this, is if you have computers on 2 different TCP/IP subnets, they can't talk to each other even if they're connected to a physical switch unless you put a router in there and you do some configurations. So if you understand that, at least is an introduction to subnetting, and I don't know, watch this 5 or 6 times in a row and hopefully you'll get everything. So that's the class on TCP/IP and subnet masking. The big thing to understand with this, if this is the first time you've ever heard of this, is, I mean, this is a confusing subject. It's one of those things, just the more you work with TCP/IP, the more you work with networking, the more this makes sense. You know, I showed you how to do subnet masking. The reality is, you don't have to do subnet masking very often. You don't have to sit down and manually create subnet masks. You need to know it in case you do ever have to do it, but this is not some daily task that you're going to be doing. I mean, like with me, you know, I come up with specialized subnets, I don't know, a couple of times a year. You just have to understand how to do it. That's really the big thing. You know, we talked about the TCP/IP protocol, that this is the TCP/IP protocol suite. Again, think of this more as an exam question. You know, you should know that it's a protocol suite, but you know, it's not that important at the end of the day. It is made up of the TCP and IP protocols. Again, IP is for the actual how computers find each other. You know, we have the IP addresses, and then TCP is how the computers talk to each other once they have found each other. The big thing with TCP is that you understand that whole concept of windowing, where the computer that is sending information will start sending larger and larger amounts of packets based on the quality of the communication lines between the two computers. As soon as it finds that there's a problem, it will then reset back to whatever the smallest number of packets is, and then start enlarging again. Again, you will not notice this for downloading videos or downloading pictures or looking at websites. You will notice this when you're dealing with voice over IP communication. Any type of real-time communication, this windowing can cause havoc with. You know, we talked about all the components of the TCP/IP networks. You have your IP address, you have your subnet mask, which divides the computers into different subnets on the same physical network. We talked about DNS and default gateways. Default gateways are basically the router that connects your little subnet to other subnets. DNS is what turns domain names into IP addresses. Remember, your computer does not care about the domain name. It cares about the IP address. We talked about DHCP, Dynamic Host Control Protocol. This is where you can have a server on the network give all the computers on the network automatic IP addresses. It does it by giving the information, and then it also gives a lease to the IP address to the computer receiving it. That lease, again, maybe one day, year, whatever you decide. At the 50% mark, when that lease has 50% expired, the computer will try to renew the lease. If it can't renew the lease, it'll go from 50% of that mark, 50% of that mark, 50% of that mark, etc. We talked about NAT, network address translation. Again, just a bit of a confusing subject. Sit down and read about it a little bit. It's not that big a deal. Basically, what NAT allows is it allows IP addresses to be reused by internal networks. So like I say, my building, everymanit.com, inside we can have IP addresses 192.168.1.3 and 192.168.1.4, etc. And you can use those exact same IP addresses. If NAT, network address translation, did not exist, that would not be possible. Every single computer or device that connected to the internet would need its own unique IP addresses. We talked about what the numbers mean. We talked about those octets. Again, when you're talking about numbers, so 10.1.10.1, that is 4 octets. Octets are combinations of 8 bits. They can either be 1 or they can be 0. You know, I showed you that whole mess. We talked about subnet masking. We talked about what used to be called class full networks, A, B, C, D, and E. Those really haven't been used since like 1992 or something. They were replaced, that whole concept was replaced by CIDR, classless internet domain routing. Again, at this level, don't worry about it. That's a Cisco, you know, when you're going off your CCNA, you know, start worrying about it then. I just want you to have heard about this since you're dealing with TCP/IP. Class full networks and CIDR, you should at least know those concepts exist. I showed you how to do the subnetting, how to find how many hosts would be on a subnet and how many subnets would be on a subnet. You know, that's all just basic math. So this class, TCP/IP and subnet masking, like I say, this isn't a hard subject. It's just something that you're just going to have to get used to. The more you deal with that TCP/IP, the more you deal with routers, the more you deal with computers, the more this will all make sense. Again, if this is your very first class, probably seems really confusing as hell, but just do some Google searches and you know, practice with your networking equipment, and you should figure it out pretty quick. So as always, I'm Eli the Computer Guy over here for Everyman IT. This was TCP/IP and subnet masking. I look forward to seeing you at the next class.